All right, welcome again, everyone, to Intro to Engineering. Today we're going to be covering Chapter 8. Chapter 8 deals with time and time-related variables. So let's do a quick discussion starter. So one of the questions for discussion starters would be, how would you define time? How would you define time? Anybody? Crickets, exactly. Like, you had a free day on Monday, pretty much. So you guys should be ready to go today. Man, you can read it out of the book. Right? You guys, you can read it out of the book. Nobody. Go ahead, Cal. Thank you for volunteering.
All right, so the definition for time, the measurement of how events take place, or I'm not entirely certain what we're looking for, actually.
No, that's just it. It's just a discussion starter. You did well. Thank you, Cal. You answered the question. Why is time important? I mean, I think it would be a part of that definition, right? Because we didn't have time or the measurement of time, then we couldn't schedule anything. Like, there would be no schedules, right? There would be no work hours. There would be no class hours. Everything would sort of be random. You couldn't like meet. It would be difficult to plan things. So, you wouldn't know your age. I mean, I think some people that probably wouldn't care though. I don't really care. Like, not knowing my age is not a big deal. But then you have some people that really care about their age, right? Absolutely right. You wouldn't know the past, present, or future. You wouldn't know what era you were in. You couldn't really define your era, the age you're living in. So time is important, right? It's important. It's important for a lot of reasons, namely those that we just talked about, right? And just to name a few more, right? How long it takes for you to get to a place, and that predicates other things such as speed. All right, like if you're trying to get to a place at a certain time, um, you gauge the speed you need to go, and then it creates other things like speed limits, right? When you're in the air, there's no speed limit. Right? If you're flying from one destination to the other, or if you're on the ocean, there's no speed limits on the ocean and in the air. And mainly because there's so much ocean and so much air, right? And you don't have very many planes in the air, and you can, because of the levels of air and you know what I mean, the radius as far as the water, you can pretty much put so many boats along the same little course and they can be riding alongside each other several miles apart, right? And so they would never collide. And so even if they're going in opposite directions, um, and same as a plane, like there's so much depth or height or however you want to look at it. The one plane can be above you and below you, right? And you wouldn't collide. It's different when you're on land because you got so many other obstacles. But anywho, I'm getting off task here because what we're talking about is time, and time is, like I said, speed is predicated on time because how fast you want to go depends on how long it'll take you to get there, how soon you need to be there. So these are the reasons as of why time is important. how much time do we have in our lives, right? And then you look at your day. Our days are 24 hours in a day because that's how long it takes for the Earth to circle around the sun. 24 hours is roughly, right? And so, or no, for the Earth to revolve, not circle around the sun. It takes a year to get around the sun, but the Earth to make one complete revolution, it takes 24 hours. Sorry, I said that incorrectly. And so we measure that, right? And so that we look at that in one day. Look at how much time in your day and how you're going to manage your time within your day. So time is very relevant. I'm not going to beat that over the head as far as the relevancy of time. What we want to look at is how does time really correlate in engineering, right? Time's role in engineering applications. Steady state. What is steady state? When the value of a physical quantity under investigation does not change. Basically, it doesn't vary. It's a constant. It doesn't move, so to speak. So that number is just that number. It's always the same. Then you have transient state, when the value of a physical quantity under investigation changes with time. So over a period of time, such as, like our bodies change over a period of time. We don't, we don't look as young as we used to. When we were adolescent, then teenagers, then early 20s. Some of you are currently in your early 20s, but there's a distinction between you and your teenage years and in your 20s. Some, not everyone, but some of you. But then when you're looking at an engineering entity, right? When you think about something as far as an engineering entity, something that would be in steady state. Anybody, could you name something that would be in steady state? A physical quantity under investigation that would be in steady state? And that quantity doesn't change? Probably not. Mass of a book, right? So if you put a weight on that book for a period of time, that book probably wouldn't change for the most part. But then you may have an indentation in the book. But is that based on time? Probably not. That would be based on the weight that's on it. Did the book hold the weight? Right. So that would be what you would look at as fatigue, not necessarily time. But another thing is like a fluid, right? If you have a pressurized fluid going through a pipe, or at a certain flow rate or what have you, that fluid doesn't change. It would remain the same. But what about a transient state, something that would change over a period of time? Weight. Well, he says we wait. Wait, what are you saying there, Mike? Oh, my weight. Does weight change over a period of time? Does weight change though? Hopefully not too much. Right. Like I think over a period of time, what does change though over a period of time? Maybe your metabolism. You know what I mean? How much your body. Oh, that's a good synopsis, right? He says your weight changes over the course of a day, and so I'm raising the question: is your weight actually changing, or is something within your body changing? Like how much you digest and how much water you drink, right? So is it time? Is it the day that's changing your weight? Or is it your consumption, how much you've digested it, waste you've gotten rid of? I'm just asking. I've never actually researched it. But that's a good assessment. That's good. That's good to provoke your thinking. Right. Definitely consumption and how much you digest, right? Weight of a child. Yeah. So that would be another good assessment. So when you think about, because children, babies, they're growing, right? So their bone structure is changing over the course of time, right? Time is growing you. You're aging in a sense. So Dina is asking, would physical growth be considered a transient state? Or trans absolutely. Like physical growth would be because to a certain point, right? And because it's mostly your bones. Because your bones are growing with time. It's changing over time, right? And your skin is obviously stretching over time. But that's the thing too with your skin is being stretched because of your bones. But once your bones stop growing, then there's no need for it to stretch. So if you consume the same amount of food and but if you consume the same amount of food and you never work out, then would your muscles grow or would you become fatter? Right? Because what makes your muscles grow and what makes fat increase in your body? Right? If you didn't exercise, would your body naturally just become so if you were just dormant, you just sat all day, obviously you probably if you didn't use your muscles, your bone density, obviously it would decrease. So if you're not working it, it's like gravity is taking a toll on you. But then unless I guess the lack of excuse me, the lack of gravity does the same because people in space they lose bone density because there's no gravity, there's no force working against. So just food for thought. Some engineering applications, electronic equipment, biomedical equipment applications, things of that nature, heating and cooling. Um, back to my handy dandy files here. So time, as someone read, the measurement of time. Time is one of the seven fundamental or base dimensions that we talked about. Last week we talked about length. Today we're talking about time. And it's good that we put it in that order because you're looking at the how long something is and then how long it takes you to do something over a period of time, right? So duration. And then the units for time, obviously, we know so many different units from minutes to seconds, years, months, days, etc., etc. Millennium, millennia, century, right? And then you have time zones, and then you have longitudes and latitudes, right? And then this is what I was expressing earlier as far as the Earth rotating, making one full revolution, 24 hours. Every 15-degree longitude corresponds to 1 hour. That's pretty cool. And you have daylight saving time, which is a waste. But some would probably argue. Some would probably argue that, right? Argue against that. And then, so the question, why do we need time zones? Obviously, right? Obviously, that's obvious. Communicating between different countries and knowing when you can and when you can't, right? But during the 19th century, railroad companies realized the need for standardizing their schedules, right? So it's just like we said earlier, but why is time important for schedule, right? So another thing to keep in mind is frequency. So when you're measuring, obviously, from just a natural sense, time it takes for an event to repeat itself. It takes about 365 days for your birthday to come around, right? But then when you think about vibrations or sine waves or things like that, and you're thinking about the period of something that is vibrating and how you would measure that, right? And how you would solve for the frequency of that, of the highest level of vibration or the lowest level of vibration or a sound wave or et cetera, et cetera. It's like using time to measure that, right? Determine when and even the peaks, determine the peak of your vibration, right? So, oh, somebody have a question? And so using time or time variables also is good to determine or develop or design sensors, right? Because you can, if you being here in Houston, all right, you can determine when the hurricane is going to hit land. And a lot of those they're basing it on sensors and they're determining the velocity the hurricane is moving at, what speed, what velocity is it traveling at, and you know what I mean, with satellite and all of that, you can determine how far out the hurricane is before it gets to land, right? How many miles away from the land it is, and then the time, and then the travel speed, and then determining, okay, it'll be on land on this day, and all of it is estimates, right? Because you're looking at or you're assuming that the velocity of the earthquake is constant. Sorry, not the earthquake, but the hurricane is constant, and that the speed won't change. But we all know that that's not true. The speed or the velocity of a hurricane changes moment by moment. Like we're predicting now, well, by the time it gets to landfall, it'll be a category 4 or category 5, and then it gets to landfall and it slows down. The resistance there. But then even sensors to determine earthquakes, right? The level of, here again, the vibrations, right? There again, like determining that to figure out what scale the earthquake is and things of that nature, the peaks and the lows, using time, which is also interesting as far as engineering. And there's you've never seen this before if you haven't been in physics, which I'm sure most of you had physics in high school. So you know the equation for the period and the frequency. All right. And then you have traffic flow. I think there is a question, or at the very least, an example about traffic using this equation. I'm not gonna go over that, but I do want to work an example eventually. I see where it is. Oh well, I think it's on down, but this is an interesting little example where K is the number of vehicles per kilometer, traffic density K, the number of cars on a stretch of a highway, and then N being the number of cars, and D being the stretch of the highway, and then you determine K based on this equation. Why is that important? Ha. Why is it important to determine the flow of traffic? Civil engineering, absolutely. Absolutely, right? How many lanes you need to develop? What are the times when traffic is most atrocious, right? When you have the most traffic. In Houston, you have your dead times, and those times are so odd. Because if you think about 59, I-10, and 45, and those are your busiest freeways here in Houston, 59, and probably in that order, 59, I-10, and 45. Because I've never seen a time that when I've been driving that 59 was just free of traffic. Like this obviously it's certain places within 59, right? Like if you're looking at 59 inside of 610 and then 59 going into Sugarland. I'm not sure if you all have been down that way. Like I don't know when there's a time when it's not busy in between 610, like coming from 288 going down near Rice Village, all the way to, let's see, probably past, honestly, probably up to the Beltway, then into Sugarland. 59 is always busy around in that part. Obviously, I-10 is so crazily busy from probably the same area, 610, in between 610, and then probably all the way to Highway to Katy to probably as Highway 90, or the Loop 99. Now we got this 99 loop. So it's determining that will help you construct your freeways, right, based on the time of day and things of that nature. But yeah. So let's get into some good stuff, such as velocity. Linear velocity provide a measure of how fast an object moves. Linear velocity. Examples. I like this. This is a good problem because we're gonna work an example on this. Let's talk about this. This is we're sitting breaking point. So average speed. It is the change in the position of moving over time. And you guys are very, very intelligent. So I'm gonna work an example with this. And we're gonna use let's say we're gonna use meters per second. All right. So average speed of an object, basically the change in position of an object over time. That's the average speed, right? So let's work an example real quick. And this is this involving linear velocity. We only have about 7 more slides, so we're gonna work this example, and then we're gonna have, I think, one more example we'll work, and then I will let you guys go. But this is based on linear velocity, and if I can find my handy dandy whiteboard. All right, here we go. Everybody can see the board? So what we want to do is determine all right, and so I'll use variables. So let's say you have an object. Right? This is the object. This object traveled a distance d from point A to B as seconds. All right, this object traveled a distance from A to B in t seconds, basically t. All right, then the same object traveled a distance from B to A 0.5 t seconds. Same distance d, obviously, right? And the question is, what is the average velocity that that object traveled at? All right. What do we need to do to work this problem? Should be really easy, right? That's pretty simple, right? Yes, you could. So what are the, so what is D? Anybody? What is D? Nobody. Ah, yes, D is the distance. But what is the answer to D? That the object traveled. So what is the total distance? Cal says, oh, 0. Is that true? Is the total distance 0? Micah said, how long did it travel? Y'all don't like variables, do you? So the total distance from A to B. What is the distance from A to B? Cal asked total displacement. No, you're making this harder than what it is, Cal. What is the Kate says V of t question? Yes, V of t, right? That's the average velocity. That's what we're trying to find, but we're gonna solve for a d first. And let me clarify. We're not solving for it numerically. We're solving for it as a variable. And what we're looking for is not d. Right, there you go. There it is. Thanks. Who was that? Was that Cal or was that John? Yeah, that was Cal. All right. So now that I 2s over 1.5d. Yeah, 2d. There you go. Thank you. So d, the total distance traveled would be 2d. Right? And then t, because it took you t seconds to get to from A to B. And then it took you 0.5 t seconds to get from B to A. So the total time, and I'm gonna put total so people won't be confused watching this video. Total D distance right, and then total time, and I'm gonna type it because that just took forever. Total time is equal to 1.5 t, and so that makes V, average V, equal 2d over 1.5 t. There it is. That's your average velocity. So the trick here is calculating the total distance traveled and the total time, right? because we said the object traveled from A to B and then from B to A. If we just said the object traveled from A to B, then it would be E over T, right? So just keep that in mind. All right. So that's another way that we use time and how time relates to in engineering. Another way is volumetric flow rate. Volumetric flow rate. So let's do a problem discussing volumetric flow rate. I guess first we will discuss volumetric flow rate. I think you guys have done the lab on volumetric flow rate, right? Oh, well, let's look at this first before we go into flow rate. All right, so we did average speed and then there linear acceleration, right? And then linear acceleration it provides a measure of how velocity changes time. All right. So your velocity changes over a period of time, and that's acceleration. Like you can go from, and if you love cars, you just like, I want to get from 0 to 60 in 2 seconds. I don't know what car can do that. Maybe a Bugatti or something, or maybe something. I don't know. Maybe a Lambo can get there faster. I don't know. Maybe I'll make that a quiz. How fast can a Lambo get from 0 to 60? How fast can a Lambo go from 0 to 60? I think I have you guys do some research on it if you don't know. And the Lambo, y'all know what a Lambo is. I mean, you guys, y'all are more hip than I am, so I know y'all know what a Lambo is. I think that'll be a good quiz. What y'all think? What do y'all think? Ha! Micah said that a race car. Lambo is that guy from Star Wars. Y'all are funny. A Tesla is faster. How fast does a Tesla go? How fast all right, we're gonna do, so cool. We'll do a little quiz. We'll do a Lambo and a Tesla. Which one goes from 0 to 60 faster? And we say 0 to 60. Why would we say 0 to 60? I know this is kind of off topic, but it's still dealing with time, right? Why do we say from 0 to 60? Why do we care about from 0 to 60? Maybe I'll make that a part of the quiz too. Like, why is our cars? There you go. See, Micah, you only succumb in speed limit, right? And so if you're idle and you're trying to get onto a service, you're coming off a service road or a feeder, or going up a ramp or something, trying to get on the freeway, and you're basically, in most cases, you may not be moving. And then if a car is like, debatable, like how far distance between you and the car that's coming up on your tail, like, I can get to 0 to 60 in like a second or two. Man, a mile a minute, right? Tesla Roadster does 0 to 60 in 1.9 seconds. I don't know how fast a Lambo goes from 0 to 60. I was just saying, guessing. Like, it may be like less than a second. I don't know. I have no idea. Ask part Al. I thought I was gonna do too much. So since y'all already answered the question, it's not gonna be a quiz anymore. I'm gonna have to give y'all a different quiz now. I'll just pick a problem out of the book. I haven't assigned a quiz yet, so I'll just pick a problem out of the book. I was gonna give you guys a freebie, but nah. Oh, see, thanks, Dina. So a Lambo, whatever, goes 0 to 60 in 2.5 seconds. What is this Tesla Roadster you were talking about, Nick? I've never heard of the Tesla Roadster.
The Roadster is supposed to be getting released, I think this next coming year, but it's a ridiculous car. I mean, the thing with Teslas is acceleration is instantaneous. You know, there's no delay like you have
Yeah, that's true.
in a combustible car. So
Yeah.
like my boss has the Model Y or something like that, and he took us in a ride in it, and going from 0 to 60 is like when you punch it, it's like
Yeah.
the equivalent of being on a roller coaster. Whenever you take off, like it literally will put you up against the back of the seat.
Hmm.
It's the power of it is something else. It's pretty cool. But the Roadster, I don't know about that other car. He just said something owl or whatever, but apparently the their
Ash
roadster
Park
is
out.
supposed, yeah, their roadster is supposed to be like the fastest 0 to 60 time of a car. Period. I think, but maybe not compared to that car he just said.
Yeah, the A
Uh,
Spark Owl is from a Japanese manufacturer saying they're boasting it at 1.69 seconds.
what does a Bugatti do then? Because the Bugattis are they used to be like the fastest cars, supposedly the fastest luxury cars on demand. We'll probably have to look that one up too. So I think I'll still make this a quiz. I'll just name a few sports cars and then have you guys look that up. I'm curious, super curious. Is the Ace Park out? Is that out? Is that on the market? Oh, a Bugatti goes 0 to 60 in 2.5. Thanks, Dina. That's like along with the Lambo.
Yeah, the Owl, I read that, or I just pulled that up off of Google from an article in 2019, November 2019. So I think it should already be out.
Okay, so they're already on the market then. Micah says his Honda can go from 0 to 60 in 2.5. Ha! That I would like to see. Yeah, Micah said me too. Yeah. I know my little Corolla, my Camry doesn't even get up to 60 in a matter of seconds. I think it takes a few minutes. I'm just kidding. I'm just kidding. That would be horrible. Who would want that on the freeway? Oh, me. All right. So acceleration. Um, the time it takes. The time it takes for you to your speed to change over time. So that's acceleration. And the VTEC. What's the VTEC? Velocity time. EC? I don't know. I have no idea. You guys with these acronyms. The racer. The racer or racer? I don't know. So then you have instantaneous acceleration, and then you have actual acceleration at a given instant. Um, and obviously, velocity and acceleration is a vector, and you all know what that is, right? The fact that it's a vector. No? Don't know what that is? Magnitude and direction. Thanks, Kyle. See, somebody's had physics. That's what makes it a vector, such as force. Force it has a magnitude and a direction. All right. Oh, it doesn't matter, Cal. I appreciate it. If you just read it or not, it's okay. So back to volumetric flow rate. Okay. As we talked about for length, right? Using length, you can determine the volume. And then using time, right? And you have a length or you have an area, you have a volume, then you can determine the volumetric flow rate. And so we all know the volume is a cubic length. And so volumetric flow rate would be a cubic length per unit time. And so let's do some analysis on a pipe. All right. So the good thing about when you're looking at a pipe, because I have so many people miss this problem on the exam, because they're not considering that it's all the velocity is flowing along the walls of the pipe, right? And you're already taking into consideration the length of the pipe because you're doing volume, right? So you don't necessarily need the length because the volume along the length doesn't change. So you only need the area, the surface area. All right. I don't know if that made sense, but you only need the surface area that the volume is, that the velocity is traveling along across, if that makes sense. Does that make sense? So to determine the volumetric flow rate, all you need is what? The surface area and a known velocity. No, yes, you with me? Maybe, no. So let's look at that. Let's look at that. Why? Does that mean yes? I'm so out of touch. So let's look at that. All right. We're looking at volumetric flow rate. We're gonna work an example of volumetric flow rate. I gotta find my whiteboard though. There it is. All right. So you have I'm gonna get this spectacular drawing going. I know you guys love my drawings. There's your pipe. All right. And you have some velocity V flowing along the walls. And then you have a diameter of V. And then this pipe is a length L. And what we're trying to determine is the volumetric flow rate. All right. So D is the diameter. So what do we need to do to solve this problem? What do we what do we need to do to solve this problem? Nobody knows? Volume over time. Okay. Well, what is little v? What is this guy? What is that? All right, velocity. And what are the units for velocity? As we're doing metric, so meters per second. Thank you. So V, so this is big V, and then little v equals velocity, which is meters per second. All right. So this is big V. So that big V, we're gonna say V dot. How about that? Let's say V dot. So we won't confuse these. V dot is equal to question mark. We don't know it. Oh, that's not V dot, that's V. It's something else. V dot. All right, V dot is equal to question mark. So what are the units for V dot? Nobody knows? So V dot is what we use for volumetric flow rate. So if you didn't know what V dot was, that's what V dot. And M dot is mass flow rate. All right. So V dot is volumetric flow rate. And it's actually like, why we call it V dot is because it's literally V with a dot. Yes. Thank you. Yes. Thanks, Micah. Thanks, Kyle. So V dot is cubic meters per second. So now that we know that, what do we need to do to solve this problem? It's real simple. What are our knowns? We know the velocity. It's V, little v. So then, what don't we know? I told you just a few minutes ago, maybe more than that. Thank you, Micah. Everybody else is asleep. We got 12 people that are in class tonight, and we got 3 people maybe awake. Now, everybody woke up when we were talking about those cars and going from 0 to 60. I think I have more participation talking about those cars than I ever have, like in all of these 2 months. Hey, I'm just kidding, guys. All right, so we need to find the area. What is the area? Know your audience. Exactly. So we're going to talk about cars more often, okay? We're going to ditch all of these other chapters, and we're going to talk about cars. That's it, okay? I'm just kidding. We're not. I don't know who the police or the ambulance are. Yeah, that's the ambulance. I don't know where they're going. They're not coming here, though. So yeah, I'm fine. Thanks for asking, guys. Appreciate it. So the area A is equal to pi b over 2. So that would be pi b squared over 4. That's the area. So then what's v dot? Since we know the area, we know the velocity, what do you need to do to get v dot? Real simple. Multiply a times velocity. Thanks, Cal. Thanks, Micah. Sorry. So we multiply a times little v. I'm sorry, Micah. You know, you and Cal have been talking the most, and I just picked up. I saw Cal. It's okay. It's okay. It's okay. Both of y'all are doing very well. Excellent. Excellent. So v dot is equal to a times little v, which turns out to be little v pi. That's not pi. Little v pi e v times v squared over 4. And voila. And there's your answer. I like variables, so sorry. But yeah, so that's it. That's time and how you use time in relation to engineering applications. All right, there's a couple more things, but I think I posted these slides. You can look over, you can read it. It's not anything too difficult. I would just be reading over it. No more examples that I want to go over. So that is it for today's lecture. Does anybody have any questions? Yes, Kyle.
So this is probably getting like ahead of our, where we currently are, but as I was reading through the chapter, something occurred to me. Do civil engineers apply any kind of fluid dynamics to like traffic whenever they are constructing the roads, or is it a different like set of principles and equations?
So I'm not gonna say they apply fluid dynamics because civils they're gonna work with mechanicals in those instances. But what they would do as a civil engineer, they would analyze materials for like when it is water on the ground or things of that nature. And so they're going to analyze like levels of how they want to construct highways that would help. You know what I mean? Like they would basically put highways or freeways in slopes so that they could have some type of drainage to keep the water from just sitting on the freeways. In other words, it's not going to be flat. In other words, you're not going to just see a flat surface. It's going to be a surface where the water can always run, in other words. And so, yeah, they would analyze it to that extent. But the fluid dynamics or flow dynamics would definitely be handled by your mechanicals.
All right, cool. Thanks.
Yeah, no problem. Any other questions? If not, I will post your quiz here shortly. And yeah, you guys have a great evening. The class wasn't too bad. It's just an hour. You're welcome, Kate. Good night, Vanessa.